You are in a room right now. Maybe it is your bedroom. Maybe it is an office. Maybe it is a late-night cafe where the air feels a little stale and the noise never fully stops. Look around and your brain does the thing it always does. It labels the walls as solid, the floor as real, the desk as heavy, your hands as yours. Everything feels dependable, like reality is made of firm objects that stay put. Now here is the uncomfortable truth. What you can see, touch, photograph, and build your entire life around is only a thin slice of what actually exists in the universe. Not a small slice in a poetic sense, a literal minority. Roughly speaking, the stuff that shines, the stuff that makes atoms and air and stars, is a few percent. The rest is invisible to your eyes and invisible to your camera. And yet it still shapes everything. That is the part people hear and shrug off like it is trivia. Okay, cool, the universe has invisible stuff. But that reaction is a defense mechanism, because if you let the idea land properly, it changes how you trust your own senses. It means your perception is not a window onto reality. It is a survival interface. Your brain evolved to spot faces, threats, food, and social cues. It did not evolve to detect the deep architecture of the cosmos. And here is where the story gets genuinely intense. Not because it is spooky, but because it is honest. The question is not whether dark matter exists. The universe has cornered us into that conclusion through multiple lines of evidence. The real question is what kind of thing it is. And the moment you ask that, a second question appears, sharper and more dangerous. What if the invisible majority of the universe is not simple? What if it has structure? To understand why that matters, imagine you are watching a dance from above, but you cannot see the dancers. You can only see dust moving on the floor. The dust forms spirals, ripples, collisions, patterns that look too coordinated to be random. You start to realize something is moving beneath the dust, something massive, something that never shows itself directly, yet forces the visible world to behave the way it does. That is our relationship with dark matter. We do not see it. We see its fingerprints. We see galaxies spinning too fast for the visible mass they contain. We see clusters of galaxies holding together when they should fly apart. We see light bending around regions of space where there is not enough luminous matter to explain the gravity. Over and over, when you do the math and you refuse to lie to yourself, you land on the same conclusion. There is extra mass, and it does not glow. For decades, physicists tried to make this invisible mass safe by assuming it was boring. A single type of particle, quiet, featureless, passive, something that only interacts through gravity, drifting through the cosmos like cosmic fog. That assumption made the problem manageable. If dark matter is simple, you can design detectors that wait for an occasional collision, a tiny flash, a faint recoil, a sign that one particle bumped into an atom. You can build an entire experimental program around one target. But the universe has a habit of punishing clean stories. The more we searched for the simplest candidates, the more reality refused to cooperate. And in science, we did not find it is not nothing. It is information. It is the universe crossing out a possibility. Each null result narrows the space where the simple story can hide. It forces theorists to stretch the model into stranger shapes, or to consider a possibility that used to sound too messy to be worth thinking about. Meta, what if dark matter is not one thing? What if it is a whole family? What if there are multiple types of dark particles, with their own interactions, their own rules, maybe even their own version of forces we know, like a hidden analog of electromagnetism that does not talk to light? This is not science fiction. This is a normal move in physics when the simplest model keeps failing. Because the universe does not owe us elegance, it owes us truth. When truth has a scary habit of being complicated. Complexity is not just an aesthetic word. Complexity changes what is possible. If dark matter can interact with itself in more than one way, it might be able to lose energy. It might be able to cool. And if it can cool, it can clump. And if it can clump, it can form structures. That step right there, structure, is the gateway drug to everything else we associate with a rich universe. Stars are structures. Planets are structures. Brains are structures. Life is structure that uses energy and information to resist decay. This is where we need one concept that sounds simple, but it is basically a trapdoor into deeper reality. Emergence. Emergence is what happens when simple things, in huge numbers, interacting for long enough, produce behavior that no single piece has on its own. A single water molecule is not wet. Wetness appears when countless molecules interact in a certain way. A single neuron is not conscious. Consciousness emerges from networks of neurons exchanging signals, building memory, predicting the future. An individual ant is not intelligent, but an ant colony can behave like a single organism, adapting and responding to threats without any ant understanding the whole plan. The universe is full of these surprises at scale. And dark matter is scale. Dark matter halos wrap galaxies and stretch across distances your brain cannot truly picture. They have been evolving for billions of years, shaping the formation of everything we can see. So even if individual dark particles are simple, the collective behavior of dark matter on cosmic scales could be complex. Not must be, but could be. And that single word is enough to change the entire mood of the story. Because the moment you admit could, you can no longer dismiss the next question as ridiculous. You can only say, we do not know yet. Sand, not knowing, is exactly where science begins. We do not have to jump to wild conclusions. We do not have to claim dark matter is alive. That would be sloppy. What we can do, and what serious researchers actually do, is ask a cleaner question. Can we test whether the dark sector is simple or complex? Can we look for indirect signatures, not of life, but of interaction? Can we compare simulations to observations and see whether dark matter behaves like a collisionless fog or something with richer internal dynamics? Does it create the kinds of halo shapes we predict? Does it produce smooth density profiles or softer cores? Does it leave subtle fingerprints in how galaxies cluster and grow? Meta. Because if we ever find convincing evidence that dark matter has internal interactions, that it can cool, that it can form more intricate structure, then dark chemistry stops sounding like a joke. And once you say chemistry, your mind naturally whispers biology. Not as a claim, as a possibility that cannot be laughed away anymore. The universe is under no obligation to limit complexity to the small, visible slice we live in. This is also why the idea feels personal, even though it is cosmic. Right now, you are sitting inside a world your senses can pass, and your brain wants to believe that what it can pass is what exists. But if most of reality is invisible, then your certainty is built on a thin film. The room around you is real, yes, but it is not the whole stage. It is a spotlight circle on a much larger theater, and the rest of the theater does not stop existing just because you cannot see it. Sex 0.5. So here is the promise of this series, and this is where we keep it disciplined. We are going to rebuild the story from the ground up, the way evidence forced it into existence. We are going to meet the astronomers who first realized the numbers did not add up. We are going to watch how the simplest explanations failed. We are going to see why the universe seems to be built on an invisible scaffold, and why that scaffold might not be featureless at all. And by the end, you will understand why some physicists can calmly say with a straight face that the most mind-bending possibility is not aliens on distant planets. It is that reality itself might be layered with an enormous hidden component shaping the cosmos while remaining almost perfectly silent to our senses. In the next part, We start with the moment the universe betrayed our expectations in a way no one could ignore, not in a philosophy book and not in a lab, but in the cold, quiet motion of galaxies. Once you see how unavoidable that conclusion is, you will never look at the night sky the same way again. If you want to understand why the dark matter might be alive idea even survived long enough to be spoken out loud by serious scientists, you have to start with a brutal fact. Dark matter wasn't invented because it sounded cool. It was dragged into existence by numbers that refused to behave. We didn't discover it the way we discover a new animal, by seeing it directly. We discovered it the way you discover a thief in your house. You don't see the thief, you see the missing money, the moved furniture, the fingerprints on a door you locked. You see effects, and the effects were everywhere. The first clue came in a place that feels almost unfairly poetic, a galaxy cluster. A cluster is not one galaxy, it's a crowd, hundreds or thousands of galaxies moving under their mutual gravity like a slow-motion swarm. When you measure how fast that swarm is moving, you can estimate how much mass must be inside it to keep it from flying apart. Sex. The problem was, when astronomers did that, the math basically screamed, there's not enough stuff here. Not enough stars, not enough gas, not enough anything visible. And yet, the cluster held together like a clenched fist. That was the moment the universe started teaching us a lesson it loves teaching. Your eyes are not a reliable census taker. The cosmos can contain something massive and real that refuses to show up in your favorite wavelength. Light is not a guarantee of existence. But one weird result doesn't rewrite physics on its own. Science has a strong immune system. It resists dramatic conclusions, and honestly, that's a good thing. For decades, people argued, maybe the measurements were wrong, maybe the assumptions were wrong, maybe gravity worked differently at those scales. And then a second line of evidence arrived, cleaner, sharper, and harder to explain away, because it showed up not in one distant cluster, but inside normal galaxies we could study in detail. Picture a spiral galaxy like the Milky Way. In your gut, you expect it to behave like a solar system. Close to the center, things orbit fast. Far out, things orbit slower. That's what happens when most of the mass sits in the middle, like the sun dominating the solar system. So astronomers measured the rotation speeds of stars and gas at different distances from galactic centers. They expected a drop-off, a graceful slowing at the edges. Meta. Instead, they found something that looks almost like the universe smiling at you while it lies. The speed stayed high. The outer parts of galaxies were moving far too fast to be held together by the visible mass alone. This is the part people underestimate emotionally, because if you take it seriously, it means galaxies are basically impossible under normal expectations. The edges should have been flung away like sparks from a grinder, but they weren't. They remained in stable orbit over cosmic time. Something unseen was providing the extra gravity, like an invisible scaffold, like a hidden halo wrapping around the galaxy and holding it together. And once you accept that, the whole universe changes texture. Reality becomes layered, not because of spirituality, not because of metaphor, because of a brutally simple idea. There is more mass than light. Now here's where the story usually gets simplified in textbooks. They'll say, okay, dark matter exists. It's invisible. It interacts through gravity. Moving on. But that moving on is exactly where the most interesting question begins. Because once you admit there's a dominant invisible component, you have to decide what kind of thing it is. And the default assumption for a long time was almost hilariously human. Physicists assumed dark matter was boring. Not boring as an insult, boring as a category, a single type of particle. Cold, slow, quiet, almost featureless. Something that mostly just drifts through space, barely acknowledging itself, barely acknowledging anything else, except through gravity. Shit, meta. And that assumption didn't come from evidence of simplicity. It came from the fact that simple models are easier to compute, easier to test, easier to build experiments for. Simple models are seductive. They make the universe feel tame. And notice what's hiding inside that assumption. We know the ordinary, visible universe is not simple at all. It's a zoo of particles and forces. It makes atoms. Atoms make molecules. Molecules make cells. Cells make brains. Invisible matter has multiple forces that let it stick together, radiate energy away, collapse into structures, and build complexity. That's how you get stars, planets, and eventually someone listening to a video at night wondering what's real. Sex 0.5. So why did we ever believe the dark sector, the part that outweighs visible matter by a lot, must be a single, lonely particle with no inner life? That's not physics. That's psychology. It's comfort disguised as caution. And here's the twist. The longer we searched for the boring version, the less cooperative the universe became. Detector after detector kept listening for that clean, simple signal, and hearing nothing. Not nothing, as in dark matter isn't real. Dark matter is real in the sense that its gravity is written into the motion of galaxies and the architecture of the cosmos. The nothing was specific. No obvious sign of the classic easy candidates behaving the way we hoped. At first, that's discouraging. But then it becomes strangely illuminating. Because every time the simplest candidate gets squeezed by new data, the space of possibilities shifts. The universe basically says, you can keep trying to force me into a simple box, or you can accept that the box might be wrong. Fuck. This is where modern thinking about dark matter starts getting spicy in a very scientific way. Some physicists began asking, what if dark matter isn't one thing? What if it's a whole dark sector, multiple particles, maybe even multiple forces, just like the visible sector? Think about that carefully, because it's the hinge of the entire could it be alive discussion. A complex dark sector doesn't mean aliens made of darkness are definitely floating through your room. It means something far more basic. Dark matter might be capable of internal interactions, not just gravitationally tugging on galaxies, but interacting with itself in ways that allow it to cool, clump, and form structures. Structure is where the universe starts doing magic without violating physics. Structure is how you go from a fog to a cloud to a star, from a star to a planet, from chemistry to biology. Now, important, this is still a hypothesis, not a bedtime story claim, not a "trust me, bro." It's an attempt to take the problem seriously. If dark matter is most of the mass, it may not be reasonable to assume it's a single, silent particle forever. And once you allow even a fraction of dark matter to be self-interacting, the mental landscape changes. Because self-interaction means dark matter could, in principle, do what visible matter does. Shed energy in its own way, collapse into denser regions in its own way, and build persistent patterns over cosmic time. Sex. That doesn't automatically equal life, but it does open the door to the only thing life really needs at the deepest level: organized complexity that can sustain itself. At this point, most people hit the brakes and say, okay, this is getting too speculative, and they're not wrong to be cautious. Science isn't about vibes. Science is about what you can test. But here's the uncomfortable part. To dismiss the idea entirely, you'd have to claim you already know what life must look like. And we don't. We only know one example: Earth life, built from carbon chemistry under visible sector forces. That's a sample size of 1. Meta. Sex 0.5. So the smarter move isn't to declare dark life is real or dark life is nonsense. The smarter move is to ask a more testable stepping stone question. Is the dark sector simple or complex? Because if it's complex, the probability space changes dramatically. Sex 0.5. And that's where we're headed next, because the next part of this story isn't philosophy. It's experiments. Deep underground detectors, giant tanks of ultra-pure material, years of data, and one brutal, recurring result. The universe keeps refusing to hand us the easy answer. Sex, which leaves us with the most dangerous possibility in science. Not that we're wrong about one theory, but that we've been asking the right question with the wrong expectations. Sex 0.5. So keep this thought in your mind as we move forward. The visible universe might be the loudest 5%, the part that screams in light. But the dark majority may not be empty. It may simply be speaking a physics we haven't learned to hear yet. And once you accept that, the line between invisible matter and invisible complexity starts to feel a lot thinner than we ever wanted it to be. Here is the uncomfortable truth about dark matter. We don't get to choose what it is. We only get to choose what questions we ask and how honest we are when the universe refuses to answer them the easy way. And for decades, the easy way was a dream scientists secretly loved. One clean particle, one clean interaction, one clean discovery. A single ghost we could finally catch in a detector, point at it, and say, "That's it, mystery solved." But the real universe doesn't behave like a neat classroom problem. It behaves like a labyrinth that keeps rearranging its walls while you're inside it. To understand why the conversation shifts from dark matter exists to dark matter might be complex, you have to follow the most relentless force in science: repeated failure. Not failure as embarrassment, failure as information. Because in physics, a null result is not nothing. A null result is a map, one more region of possibility shaded out in ink. For a long time, the leading idea was that dark matter is made of particles that are heavy enough to matter gravitationally, and that occasionally, very rarely, they might bump into ordinary atoms. Not enough to glow or burn or reflect light, but enough to leave a tiny signature in a quiet detector. That's the logic behind direct detection experiments. You build a chamber of extremely pure material, isolated from cosmic rays and radiation, bury it deep underground, and you wait. The waiting is the point, because if your detector is noisy, you'll hallucinate signals. You'll see patterns that aren't real. In a field like dark matter, where everyone wants a discovery, the greatest danger isn't missing the truth, it's accidentally inventing it. So these experiments are designed like confessionals. They demand silence. They demand patience. They demand that the universe speak in a whisper. And what did we hear? Over and over, the same answer. Nothing definitive. Limits got tighter. Sensitivity improved. Background noise dropped. The equipment became more beautiful, more obsessive, more nearly perfect. And still, no clean, undeniable collision that everyone agreed was dark matter. It's tempting to interpret that silence as disappointment, but the say-it-out-loud reality is, if dark matter were the simplest kind, the kind we built decades of experiments to find, we might have expected to see it by now. Not guaranteed. Science doesn't do guaranteed, but expected. Reasonably expected. The fact that we keep not seeing it doesn't prove dark matter is alive or intelligent or anything dramatic. It proves something more precise. Our favorite simple story is increasingly constrained. Sal, here's where the universe gets clever. Because dark matter doesn't only show up in detectors. It shows up in the sky, in the way mass bends space-time, and in the way space-time bends light. Gravitational lensing is one of the most brutally honest phenomena in astronomy. You don't have to believe a story. You can measure an arc of distorted light around a galaxy cluster and infer mass the way you infer the shape of a hand by the shadow it casts. Lensing tells us dark matter is not just a mathematical trick. It behaves like a real distribution of mass. It forms halos. It clumps on large scales. It creates scaffolding that ordinary matter falls into. Without that scaffolding, galaxies wouldn't have assembled as quickly as we see them assembling in the early universe. The visible cosmos is basically built inside a dark architecture we cannot see. And that architecture isn't perfectly smooth. It has substructure, it has hierarchy, it has patterns within patterns. Some of that complexity might come from ordinary astrophysics, gas dynamics, star formation, supernova feedback. But some of it could be whispering something else, that the dark sector may not be a single, simple ingredient. This is the point where a lot of people's intuition breaks, because they think complex means mystical. It doesn't. Complex in physics can simply mean more than one piece, more than one particle, more than one interaction, more than one way to move energy around. Sex 0.5. In the visible world, complexity isn't optional. If you try to describe everything you see as one kind of particle with one kind of force, you instantly fail. We need a whole catalog, electrons, quarks, photons, and multiple forces to bind them, move them, and let them radiate away energy. Radiation is key because it's how structure forms. A cloud collapses into a star because it can lose energy, because it can cool. A system that cannot cool cannot collapse into rich structures easily. So when physicists ask whether dark matter might have its own dark radiation, they're not writing sci-fi. They're asking a clean, mechanistic question. Can dark matter shed energy somehow inside its own hidden rules without talking to our light? If yes, then a fraction of it might behave very differently than the cold, inert, forever drifting picture. #meta, sex 0.5. Even a small fraction matters. That's the subtle, terrifying part. You don't need all dark matter to be interactive to change the story. You only need enough to create new kinds of structures, denser regions, disk-like distributions, or compact clumps that behave unlike the standard smooth halo assumption. 0.5. And here is where the idea of emergence stops being a philosophical buzzword and becomes the heart of the tension. Emergence is what happens when a system becomes large enough, old enough, and richly interacting enough that its collective behavior cannot be reduced to one component's behavior. A single water molecule isn't wet. Wetness is an emergent property of many molecules together. A single neuron isn't conscious. Whatever consciousness is, it emerges from networks. A single ant isn't a colony. A colony behaves like something else entirely. Not magic, just many simple rules interacting at scale. So the moment you grant the dark sector the possibility of internal interactions, of structure formation, of cooling channels, of multiple species, you open the door to a truly unsettling question. Not is dark matter alive, but could dark matter support emergent behaviors at scales we've barely begun to model? Because dark matter halos are not small, they are massive on a scale that laughs at human intuition. They're ancient. They've been evolving since the early universe. They have had billions of years for patterns to develop, stabilize, and transform. If there is any mechanism at all for dark matter to form rich internal structure, then we have to admit we don't know what the long-term ecology of those structures could look like. Meta. Now, skeptics will say, stop, you're sliding from physics into fantasy, and that warning is healthy. But notice what the skeptic often assumes without realizing it. They assume we would recognize life if it existed, that we would know what signature to look for. We wouldn't. If dark matter barely interacts with ordinary matter, it won't produce the classic biosignatures we use in astrobiology. No oxygen lines in an atmosphere, no methane anomalies we can easily read as metabolism, no radio emissions necessarily, no visible artifacts. Dark chemistry, if it exists, could be completely electromagnetically silent. The most frustrating possibility is that dark complexity could be everywhere and still leave us with only gravitational clues, like footprints in snow we can't walk on. So the honest scientific path is to back up one step and focus on what we can test. Not, is it alive, but is it simple? Not, does it think, but does it interact? Not, does it have biology, but does it have structure beyond the standard model? This is why the modern frontier is starting to feel like a fork in the road. One road says, keep hunting the simplest particles harder and deeper, because maybe we're just unlucky so far. The other road says, consider that the dark sector might be a whole hidden world of physics, and our detectors are tuned to hear only one narrow note. And that second road leads to a strange kind of humility, because if dark matter is not one particle, but a spectrum of possibilities, multiple species, hidden forces, maybe even dark analogues of photons, then our failure to detect it directly isn't a sign that nature is empty. It's a sign that nature is refusing to speak in the language we built our instruments to understand. There's another reason this matters, and it's psychological as much as scientific. We humans have this habit of treating the visible universe as the real one, and everything else as a footnote. But if the majority of mass is dark, then the visible universe might actually be the footnote. A thin, luminous foam riding on top of a deep ocean of invisible structure. And oceans have currents. Oceans have layers. Oceans have ecosystems. Even without claiming dark matter is alive, the analogy hits for a reason. When you scale up matter, time, and interaction, new behaviors appear. If the dark sector has even a fraction of the richness the visible sector has, then something like dark structure becomes almost unavoidable. Which brings us to the next question, the one that decides whether this whole story stays a speculation or becomes a serious probability shift. What would complexity in the dark sector do to the universe we can actually observe? How would it reshape halos? How would it alter galaxy formation? How would it leave fingerprints in the cosmic web, in lensing maps, in the cosmic microwave background, in the smallest galaxies at the edge of what we can measure? Because if dark matter is truly just cold and inert, the universe should look one way. If dark matter has an interacting fraction, the universe should look subtly different. Cores, where we predict cusps, distributions that don't match the simplest simulations, anomalies that persist even after we account for ordinary baryonic physics. Those differences are not glamorous. They won't show up as a headline that screams, "Aliens confirmed." They'll show up as small statistical tensions, persistent mismatches, patterns that won't go away no matter how much you polish the model. And in science, that's how revolutions begin, not with fireworks, but with irritation. So in the next part, we're going to follow those irritations, the places where simple dark matter models start to feel slightly wrong, the places where the universe seems to be hinting, quietly, that the dark sector may have depth. And once you see that depth, the alive question stops sounding like a joke. It doesn't become an answer, but it becomes a door you can no longer pretend isn't there. Sex. Because the most dangerous thing in physics is not a wild idea. It's an idea that might be true, and might be testable, and might force you to admit that reality is bigger than your senses, bigger than your instruments, bigger than your comfort. And dark matter has been doing that to us for nearly a century. The first place the simple story starts to wobble isn't in a lab. It's in the quiet, inconvenient corners of the sky. Tiny galaxies that should be boring, but refuse to behave. If you run the cleanest simulations with standard cold dark matter, you get a very specific prediction. Dark matter halos should be densest at the center, rising into a steep cusp, like a mountain peak. That's not a poetic description. It's the math of gravity playing out over billions of years. Cold, collisionless particles fall inward, and nothing stops them from piling up. But then astronomers measure real dwarf galaxies, small, dim systems orbiting bigger galaxies like the Milky Way, and many of them don't show cusps. They look more like cores, flatter, softer centers, as if something pushed the dark matter out of the middle. This mismatch has a name that sounds harmless, but isn't: the cusp-core problem. It's one of those phrases scientists use when they're trying not to scream. Now, there's a completely ordinary explanation that could save the simple story. It's called baryonic feedback, which is a fancy way of saying normal matter can be violent. When stars form, when supernovae explode, gas can be blasted outward and then fall back in. That repeated breathing, out, in, can reshape the gravitational field and stir the dark matter, smoothing a cusp into a core. That explanation is real. It works in many cases. It might be doing a lot of the heavy lifting. But here's the reason this becomes a cliffhanger instead of a tidy resolution. Some dwarf galaxies are so small, so faint, and so star-poor that they shouldn't have enough explosive power to sculpt their dark matter that dramatically. And yet, in some observations, the cores seem to persist. So you get this uneasy choice. Either our understanding of feedback is incomplete, even in tiny galaxies, or the dark matter itself has properties we've been refusing to consider. Not magic properties, just physical ones, the kind that would make it less like a ghost and more like a substance. This is where one alternative steps into the spotlight, not because it's glamorous, but because it's practical: self-interacting dark matter. The idea is brutally simple. What if dark matter particles can collide with each other sometimes? Not often enough to light up or bind into atoms the way our matter does, but enough that, over cosmic time, those collisions redistribute energy inside halos and puff up the dense centers into cores. That one tweak changes the feel of the universe. Collisionless dark matter behaves like an invisible swarm of bullets passing through each other forever. Self-interacting dark matter behaves more like an invisible fluid, still mostly transparent, still mostly uncapturable, but capable of internal thermal behavior. Heat can move. Density can relax. Structure can soften. And once you start thinking in terms of internal behavior, you begin noticing other cracks in the simple picture. Another famous one is the missing satellites problem. Standard simulations predict that a galaxy like the Milky Way should be surrounded by a vast population of small subhalos, hundreds, maybe thousands, many of which should host tiny satellite galaxies. For a long time, we saw far fewer satellites than predicted. Over the last couple decades, that gap has narrowed because surveys improved. We found more faint dwarfs. We realized many subhalos might exist without enough gas and stars to be visible. So this problem too might be explainable inside standard physics. But even here, the tension didn't just disappear. It mutated into something more specific and more unsettling. That mutation is called too big to fail. Simulations predict that some of the most massive subhalos around the Milky Way should be dense enough in their centers that they almost cannot avoid forming visible galaxies. They're too big, too gravitationally deep to remain dark. And yet, when we look for the corresponding bright satellites, they aren't there in the numbers and densities we'd expect. Again, baryonic physics might solve this. Maybe the Milky Way's formation history, tidal stripping, feedback, and environment are more complicated than the simple runs assumed. But the deeper point remains. Every time these small-scale issues persist, they whisper the same message. The dark sector might not be one particle and nothing else. It might have internal knobs, interaction strengths, mass ranges, or even multiple components. Now, if you're skeptical, good. Because the universe is messy and observations are hard, and there's an embarrassing amount of uncertainty in measuring the inner density profiles of faint galaxies. But skepticism cuts both ways. You should be skeptical of dramatic claims. You should also be skeptical of our own comfort. And comfort is exactly what the simplest cold dark matter model gives us. A clean, elegant baseline. It's a workhorse. It's powerful. It explains the cosmic web, large-scale clustering, and the overall growth of structure remarkably well. That's why it's lasted. But the small-scale weirdness keeps dragging us back into the uncomfortable zone where we have to ask, is the baseline missing a hidden layer? Here's where the story gets sharper, because self-interactions are not a free pass. If dark matter collides too strongly, it would leave signatures we'd already have noticed, especially in systems like colliding galaxy clusters. And there is one cluster collision that has become almost mythic in cosmology: the bullet cluster. In the bullet cluster, two galaxy clusters slammed through each other. The hot gas, ordinary matter, experienced drag, heated up, and lagged behind. But gravitational lensing maps showed most of the mass passed through, staying aligned with the galaxies rather than the gas. The classic interpretation is that dark matter behaved collisionlessly, like something that doesn't get slowed down by impacts the way gas does. People love to treat the bullet cluster like a courtroom verdict. Dark matter is collisionless, case closed. But reality is always more nuanced. The bullet cluster constrains how strong those self-interactions can be. It doesn't necessarily force them to be exactly zero. There's still room, depending on the model, for dark matter to have interactions weak enough to slip through cluster collisions, yet strong enough to reshape dwarf galaxies over billions of years. So we're left in a strange middle ground. The simplest picture works beautifully on large scales. Some smaller scale data suggests it's not the whole story. And some independent constraints tell us if we modify dark matter, the modification must be subtle, disciplined, and consistent with gravity's harsh accounting. At this point, you might think the safe conclusion is, fine, dark matter is still boring, just slightly less boring. But notice what's happening. The moment you allow even a small amount of internal physics, collisions, hidden forces, dark radiation, you stop living in a one-particle universe. You start living in a sector, a dark sector. And sectors can contain chemistry-like complexity without ever touching our light. This is where the alive question becomes psychologically sticky. Not because we've proven anything alive exists. We haven't. The sticky part is that complexity is a slippery slope in the universe. Complexity doesn't guarantee life. But life, as far as we know, emerges most readily where there's a rich space of interactions and stable structures. In ordinary matter, those structures are atoms, molecules, membranes, networks. In a hypothetical dark sector, the structures could be completely different and still capable of long-lived organization. Think of it like this. Imagine you're trying to understand a city from far away at night, but you can't see the buildings. You can only see how the traffic flows. If the traffic always flows like a perfectly random swarm, you'd infer there are no roads, no rules, no structure. But if the flow has patterns, rush hours, bottlenecks, stable loops, you'd start suspecting an underlying infrastructure you can't directly observe. That's what these halo anomalies are, at their most honest. Possible patterns in the traffic of gravity. They don't scream dark cities. They don't even prove dark roads. But they make it harder to keep saying, with confidence, that the dark sector is featureless. And the best part is, this doesn't have to stay philosophical. If dark matter has self-interactions, it changes the shapes of halos. It changes how subhalos survive. It changes how merging systems relax. Those changes can be tested statistically across large populations of galaxies and clusters. Which means the next phase of this story isn't someone has a wild idea. The next phase is surveys and measurements become so precise that the universe is forced to pick a side. Either the small-scale tensions fade as we understand baryonic physics better, or they remain stubborn even after we account for everything visible. And then we're left staring at the dark sector as the source of the discrepancy. So here's the hook you should hold on to as we move forward. We are not arguing about aliens. We are not arguing about invisible civilizations. We are arguing about something far more grounded and far more dangerous to our assumptions. We are arguing about whether the dominant mass of the universe is a passive background or an active medium with its own internal dynamics. Because if dark matter has dynamics, then it can have history. And if it has history, it can have evolution. Maybe not biological evolution, but evolution in the broader sense. Structures forming, interacting, stabilizing, breaking, reforming, becoming more intricate over time. In the next part, we're going to follow the most provocative thread of all, the possibility that the dark sector doesn't just have self-interactions, but multiple components. Dark forces, dark radiation, maybe even dark cooling. And cooling is the hinge of complexity. Cooling is what lets chaos become architecture. Once you understand why cooling matters, you'll see why some physicists get that uneasy, almost haunted look when you ask them whether the dark universe could be more than scaffolding. They won't say yes. They can't. But they also can't say no with the confidence they used to have. And that shift, just that tiny shift, is where this entire story becomes impossible to unsee. There is a single word that quietly separates a universe that stays fuzzy from a universe that learns to build structure. That word is cooling. In ordinary matter, cooling is the reason a cloud of gas can stop being a cloud. It's why chaos becomes architecture. A hot gas has pressure. Pressure fights gravity. If the gas can't shed energy, it can't settle. It can't collapse into a disk. It can't fragment into stars. It remains a swollen, featureless haze. But if it can radiate energy away, if it can cool, then gravity starts winning, slowly but relentlessly, and complexity begins. That is the hinge. Not intelligence, not biology, not life. Cooling. The ability for a system to lose energy and tighten its shape. Now ask the forbidden question in the most scientific way possible. Can the dark sector cool? If dark matter is truly collisionless, particles that only feel gravity, then it does not cool in the way ordinary matter cools. It can fall inward and form large halos, but it struggles to create thin, dense structures. It stays puffed up, smooth, diffuse, a cosmic fog that acts like scaffolding but never becomes a building. But if even a fraction of dark matter can interact with itself, then a new set of possibilities opens. And the most important of those possibilities is this. The dark sector might possess its own way to carry energy away, a dark analog of radiation, a dark photon, a dark field that can transport heat the way light does for us. If that exists, then the dark sector can, in principle, do what ordinary gas does: cool, collapse, flatten, and form structures that are not just halos, but disks, clumps, maybe even dense objects. This is why some physicists talk about a partially interacting dark matter model. The idea isn't that all dark matter behaves like ordinary matter. That would have been obvious long ago. The idea is more surgical and more unsettling. Most of dark matter could remain cold and collisionless, forming the familiar halos that match large-scale observations, while a small fraction, a minority component, could have richer physics. It could collide, dissipate energy, and become organized. If you're trying to keep your feet on the ground, here's the grounded version. A minority dark component that cools could settle into a thin dark disk inside galaxies, aligned with the visible disk, because that's where angular momentum and gravitational potential naturally guide dissipative matter. The Milky Way could have, hidden inside it, a shadow structure, not a second visible galaxy, not a glowing mirror world, but an invisible mass distribution that is flatter than the halo. You don't need science fiction to see why that matters. A dark disk would change gravity in a very specific way, not at the scale of atoms, not at the scale of people, but at the scale of stars moving through the Milky Way's plane. It would subtly alter how stars bob up and down through the galactic midplane. It could affect the vertical structure of the disk, the motion of stellar populations, the evolution of spiral arms, the heating of star orbits over cosmic time. We can't see the disk, but we can see what gravity does to visible matter. That's the whole game. And there is something quietly thrilling about this. The hypothesis is constrainable. If you add too much mass into a thin, dark disk, you would distort stellar motions in ways that don't match what we measure. If you add too little, it becomes irrelevant. So there is a measurable window where it could exist. It's not anything goes. It's physics with a tight leash. But then comes the deeper implication, the one that makes the story feel like it's leaning over an edge. Cooling is not just a structural trick. Cooling is the permission slip for chemistry-like behavior. In ordinary matter, once you have radiative cooling and stable bound states, you get atoms. Once you have atoms, you get molecules. Once you have molecules, you get complicated networks of reactions. Most of those networks are not life. But some of them become self-sustaining, information-bearing, adaptive systems. Life is not guaranteed, but the space of possibilities becomes enormous once you have stable building blocks and ways to shed energy. So the honest, careful statement is this. If a dark sector contains multiple particle types, and if it contains a force that creates bound states, dark analogues of electromagnetism, then the dark sector could support dark atoms and dark chemistry. That phrase sounds like fantasy, but it's simply the logical extension of there exists a dark force that binds charged particles into stable composites. Physics does not reserve bound states for visible matter. It allows them wherever the right forces exist. At this point, you might feel the trap closing. If dark atoms are possible, then dark molecules are possible. If dark molecules are possible, then dark complexity is possible. And if dark complexity is possible, the question of could it ever become lifelike stops being absurd and becomes statistical. Not certain, not proven, but no longer dismissible on purely physical grounds. Now, to keep our credibility intact, we have to say the uncomfortable part out loud. We do not know if any of these dark forces exist. We do not know if dark photons exist. We do not know if there are two stable dark particle species with opposite dark charges that could form atoms. And we do not know whether dark matter can dissipate energy efficiently enough to create thin structures. But we can ask, if it did, what would the universe look like? And this is where the story tightens into something you can almost feel in your bones. Because a dark disk, or dark cooling, or dark self-interactions are not just philosophical flourishes. They leave fingerprints. They alter halo shapes. They alter the distribution of satellites. They alter how galaxies merge. They alter gravitational lensing maps in subtle ways. They alter the statistics of structure formation. The universe becomes a crime scene, and gravity is the detective that never lies, only the witness that's hard to interview. There's another reason the cooling idea is so pivotal. It offers a bridge between two worlds of evidence that usually live far apart. On the one hand, you have particle physics experiments, underground detectors, colliders, precision measurements searching for new particles and new interactions. On the other hand, you have astrophysics, galaxies, clusters, lensing, and the cosmic microwave background, the ancient afterglow of the Big Bang. A complex dark sector could show up in both. If dark matter interacts with itself, halos could develop cores rather than cusps. If dark matter has a dissipative component, you might see disk-like mass distributions. If dark matter couples to a dark radiation field, it could affect early universe dynamics, leaving subtle imprints in cosmological data. If dark matter includes multiple components, you could see small deviations from the clean predictions of the simplest model. Not enough to break the universe, but enough to suggest it has more gears than we assumed. And now the tension becomes almost cinematic, because we've been searching for the simplest kind of dark matter for decades. The results have become increasingly constraining. Many of the clean, elegant candidates have been squeezed into smaller and smaller corners of possibility space. That doesn't mean dark matter isn't real. It means our favorite story about what it is might be wrong. When the simplest story keeps failing tests, science does what it always does. It stops being sentimental. It starts considering the messier truth. A complex dark sector is messier. It has more parameters, more models, more ways to hide. In one sense, that's frustrating, because it makes the hunt harder. But in another sense, it's exactly what you should expect if the universe isn't obligated to be simple just because we find simplicity beautiful. Here is the part that most people miss. Complex does not mean convenient. Complexity is not an excuse. It's a prediction with consequences. If there is a dissipative dark component, it can't be too large, or it would have already revealed itself gravitationally in ways we would recognize. If dark self-interactions exist, they can't be too strong, or cluster collisions and halo shapes would look wrong. If dark radiation exists, it can't contradict early universe constraints. The dark sector can be richer than we assumed, but it cannot be arbitrary. The universe is generous with wonder, but strict with bookkeeping. And yet, within those constraints, there is room for something that feels like a twist ending waiting to happen. Because once you accept that a small fraction of dark matter might cool, you have to accept what cooling enables. Structure formation beyond halos. Not just diffuse clouds, but dense, long-lived arrangements. And long-lived arrangements are the soil where emergent behavior grows. This is where alive becomes a scientific provocation rather than a science fiction headline. We're not saying there are dark organisms. We're saying that the ingredients that generate complexity in our sector, multiple particle types, forces, bound states, cooling channels, could, in principle, exist in the dark sector. If they do, then the dark universe is not just empty scaffolding. It is a medium capable of forming intricate patterns over billions of years. And if you give a medium billions of years, vast scales, and the ability to form stable structure, you should at least entertain the possibility that something interesting might emerge. Interesting might mean clumps. It might mean dark stars. It might mean dark chemistry. Or it might mean something we don't have words for, because our words were built for light and atoms and the narrow slice of reality we evolved to perceive. Here is the strangest part. We might already be brushing against the edge of this without realizing it. When astronomers map the Milky Way's gravitational field, when they measure how stars oscillate above and below the galactic plane, when they infer the mass distribution near the disk, they are, in a sense, listening for a hidden layer. They are listening for the possibility that the galaxy contains an invisible structure nested inside the visible one. Even if the answer is no, the search changes how we see ourselves. It forces us to admit that we live inside a gravitational environment dominated by something we do not understand. We are not floating in empty space. We are swimming through an ocean of mass whose nature remains unknown. Every star you've ever seen is a bright foam on the surface of a much deeper sea. Now, let's take one careful step further, because the next idea is where the whole story starts to feel like the universe is looking back. If the dark sector can cool and form structures, those structures could evolve. Not biologically, necessarily, but dynamically, over time, through mergers, collapses, fragmentation, stabilization, through the slow selection of stable configurations out of a vast space of unstable ones. That is a form of evolution, not DNA, but the physics of patterns persisting. Life, at its most abstract, is a pattern that maintains itself against entropy by exploiting energy gradients. It takes in free energy and uses it to preserve structure and replicate or propagate. You don't need carbon for that definition. You need dynamics. You need gradients. You need mechanisms. We have no idea whether the dark sector provides those, but if it can cool, if it can form bound states, then it is at least capable of the kind of organization that makes the question worth asking. So here's the cliffhanger the P5 is building toward. If the dark universe can cool, then the dark universe can build. If the dark universe can build, then the dark universe can develop structure that persists. And if structure persists for billions of years, then emergence is no longer a human privilege. It becomes a cosmic habit. In the next part, we're going to sharpen this into a testable direction. How would we detect a complex dark sector without ever touching it directly? What gravitational signatures would betray it? What would a dark disk do to stellar streams? What would self-interactions do to halo collisions? What would dark cooling do to the architecture of galaxies? Because the story is about to pivot from what if to how would we know, and once you start asking how you would know, the dark stops being a metaphor. It becomes a target. If the dark universe is complex, we don't get the luxury of seeing it with a telescope. We don't get spectra. We don't get glowing nebulae. We don't get chemical fingerprints. We get one thing and one thing only: gravity. And gravity is a weird witness. It never lies, but it speaks in silhouettes. So P6 is about a brutal question. How do you detect complexity in something that refuses to interact with light? You start by looking for places where the simplest story, cold, collisionless dark matter, predicts one pattern, and the universe keeps showing you another. Not wildly wrong, not physics is dead, just off. The kind of off that makes serious people stop smiling and start measuring twice. The cleanest version of the simple story says dark matter forms halos with specific density profiles. Those profiles should rise steeply toward the center, creating what simulations often produce: a sharp central cusp. But when we look at many small galaxies, especially dwarf galaxies, their inner mass distributions often look flatter, more like cores. This is the famous cusp-core tension. It's not a slam dunk. Astrophysics is messy. Feedback from stars and supernovae can puff up the inner regions and mimic a core. But what matters is that the door stays open. If dark matter has self-interactions, it naturally smooths out cusps into cores. That's the first tell. Self-interactions would make halos behave less like a collisionless gas and more like a medium that can redistribute energy internally. Not enough to glow, just enough to reshape itself. The second tell is even more dramatic because it comes from the most cinematic events in the cosmos: cluster collisions. When two galaxy clusters smash through each other, the visible gas slams, heats up, and emits X-rays. The galaxies themselves mostly pass through like bees in a swarm. Dark matter, in the simplest picture, should pass through too, because it doesn't collide. And in famous systems like the Bullet Cluster, gravitational lensing maps place most of the mass where the galaxies went, not where the hot gas is. That is one of the strongest pieces of evidence that dark matter is real and behaves mostly collisionlessly. But here's the twist. Mostly collisionless is not the same as perfectly collisionless. A small amount of self-interaction could, in principle, cause subtle offsets. A drag, a reshaping, a lag between where galaxies go and where the dark mass peak sits. People look for these effects because they're like scratches on a fingerprint. If you found consistent offsets across many collisions, you'd have evidence that dark matter does more than just drift. And then comes the third tell, the one that ties directly to your dark disk idea from P5. The vertical motion of stars in the Milky Way. If there is a thin dark disk nested in our galaxy, it would add extra gravity near the plane. Stars above the disk would feel a slightly stronger pull toward it. Their up and down oscillations, how they bob through the galactic plane, would change. Not in a way you can see with your eyes, but in a way you can detect statistically with precise stellar motion data. This is why big surveys matter. This is why mapping billions of stars isn't just pretty, it's forensic work. A dark disk would also affect stellar streams. Long ribbons of stars torn from smaller galaxies and globular clusters stretched around the Milky Way like cosmic spaghetti. Streams are unbelievably sensitive to the galaxy's gravitational potential. If the potential has an extra flattened component, streams precess differently. They warp. They fan out in characteristic ways. In other words, streams are like seismographs for invisible mass. Now, notice what's happening. None of this requires believing in dark life. It doesn't even require believing in dark atoms. It just requires admitting one possibility. The dark sector might have more internal physics than we assumed, and that internal physics could reshape mass distributions. So the hunt becomes, find gravitational signatures that are hard to explain with ordinary baryonic processes alone. But there's a fourth tell that's even deeper, because it reaches back to the early universe, back to the first light we can still observe, the cosmic microwave background, the CMB. In the early universe, everything was hot and dense. Ordinary matter and radiation were tightly coupled. Photons bounced off electrons, keeping the plasma smooth in certain ways and creating acoustic oscillations. Dark matter, in the simplest picture, did not participate in that plasma. It just sat there gravitationally, helping structure grow. That separation between coupled and uncoupled is written into the CMB's pattern like a fossil. If the dark sector includes dark radiation, dark photons or something similar, then the early universe dynamics change. You get additional relativistic degrees of freedom. Cosmologists parameterize this as something like extra effective neutrino species, because it behaves similarly in the equations. Measurements of the CMB and Big Bang nucleosynthesis constrain that. Again, not arbitrary. The universe is strict with bookkeeping. So, if you want a testable path to dark complexity, it looks like this. Self-interactions and dissipative behavior should leave gravitational footprints in halos, collisions, streams, and early universe relic radiation. That's the honest map. Now, here's the moment where the story becomes psychologically sticky, the moment that makes people keep listening. Because when you think about it, our entire strategy for decades has been to catch dark matter like it's a particle that occasionally bumps into a nucleus. That's why underground detectors are built like cathedrals, ultra-pure, ultra-quiet, hidden under mountains. The problem is, if dark matter doesn't like to bump nuclei, if it's lighter or more weakly coupled, or lives in a richer sector with forces that don't talk to us, then these experiments can run for years and see nothing, and the universe hasn't contradicted itself at all. We're just trying to hear a whisper with the wrong microphone. Null results don't prove dark matter is complex, but they do something psychologically important. They remove our favorite simple options one by one, pushing us toward less convenient, more layered explanations. And then there's the eerie symmetry you can't unsee once you notice it. We keep assuming complexity must announce itself through light, through chemistry, through radiation, through electromagnetic signatures. That's how complexity behaves in our sector. But gravity doesn't care about your preference. If complexity can arise in a medium that does not emit light, then complexity could be everywhere and remain invisible. It would still sculpt the universe. It would still leave patterns. It would just never glow for us. This is why the alive question is so slippery. If dark matter has no electromagnetic coupling, dark life, if it existed, would have no biosignatures we know how to detect, no oxygen absorption lines, no methane out of equilibrium, no radio chatter, no lasers, none of the things SETI listens for. It would be like trying to detect fish by scanning the ocean for bird songs. So we pivot the goal. We stop asking, can we detect dark life? And instead ask, can we detect dark complexity? Because complexity is the prerequisite. If the dark sector is simple, lifelike emergence becomes far less plausible. If the dark sector is rich, multiple particles, forces, cooling channels, then emergence becomes less like fantasy and more like a probability question. But we're not there yet. Right now, we're still in the detective phase. We are searching for contradictions between the simplest story and the observed universe, and then asking whether dark self-interactions, dark disks, or dark radiation could resolve them without breaking anything else. And that's why the next step matters more than any spooky speculation, because it tells you whether this entire line of thought is grounded or just hypnotic storytelling. So in P7, we're going to push into the hardest part. What does it even mean to call something alive when it doesn't use atoms, doesn't use chemistry we know, and doesn't share our sensory channels? We're going to define life in a way that doesn't smuggle in Earth bias. Then we'll ask what properties a dark system would need to meet that definition, and whether any of those properties could ever be indirectly observable, through gravity, through structure, through cosmic evolution. Because the most unsettling possibility isn't aliens out there. It's that the universe has been running two kinds of complexity at once, one that glows and one that never had to. And we've been staring at the bright 5% like it's the whole story. If you want to keep this grounded, we have to do something humans are hilariously bad at. Define life without sneaking in Earth as the template. Because the moment you say cells or DNA or water, you're not doing science anymore. You're doing nostalgia. So let's strip it down to the bones. Life, at the most general level, is a pattern that resists equilibrium, a structure that stays organized even though the universe is constantly trying to smear everything into sameness. It does that by processing energy, maintaining boundaries, storing information, and adapting across time. Not romance, not poetry, just thermodynamics plus evolution. And now, here's the part that makes people swallow hard. That definition doesn't care what you're made of, carbon or silicon, atoms or something else, light-based chemistry or a dark sector analog. Life is not a substance. Life is a behavior. So the real question becomes, could the dark sector support behaviors like that? To answer it, we have to understand what would even count as dark chemistry. Not in the literal sense of molecules we can smell or touch, but in the abstract sense. Stable building blocks that can bind into larger structures, interact in rule-governed ways, and create long-lived networks that can store and transform information. In ordinary matter, that comes from electromagnetism binding electrons to nuclei, and from the immense combinatorial playground of molecular bonds. In the dark sector, if there are dark charges and a dark force carrier, call it a dark photon or something analogous, then in principle, you can get dark bound states, dark atoms, dark molecules. The names sound like sci-fi, but the idea is simple. If there's a force and there are charged particles under that force, you can form structures. Structure is the seed. But structure alone isn't life. A crystal is structured, a snowflake is structured, a spiral galaxy is structured. Life is structure with a job: persist, replicate, adapt. So we need three ingredients. First, an energy gradient. Life lives off imbalance. On Earth, sunlight and geochemistry create gradients: hot to cold, high potential to low potential, oxidized to reduced. In a dark sector, what would play the role of sunlight? It could be something like dark radiation, or transitions between dark-bound states that release energy, or energy extracted from gravitational potential as dark matter clumps. If a subset of dark matter can cool, meaning it can lose energy through dark interactions, then it can fall into denser states. That process itself creates gradients: dense versus diffuse, hot versus cold, high potential versus low. Second, information storage. Life is not just a chemistry, it's a memory. You need something that can encode how to build me again, and you need that code to be copied imperfectly so evolution can happen. In our world, DNA is one way, but it's not the only logically possible way. Any system that can maintain a stable, copyable pattern, self-templating chains, interacting networks, repeating motifs, could, in theory, function as heredity. This is where the dark life idea becomes both possible and horrifying, because heredity is an algorithmic concept, not an Earth-only chemical trick. Third, selection pressure. There has to be competition or filtering, Some patterns persist better than others. Over time, that produces adaptation. In a dark sector, selection could happen inside dark halos, inside hypothetical dark disks, inside dense clumps. Patterns that manage energy better survive. Patterns that replicate faster dominate. Patterns that stabilize against disruption outcompete others. That's Darwin in its most minimal form. Now, here's the pivot that keeps this from drifting into pure imagination. We ask what such a system would look like from the outside, using only gravity as our window. Because if dark life is real and interacts with us only gravitationally, then you won't see it with a telescope. You won't detect its chemistry with spectroscopy. You won't catch its signals with radio. You would only see it if it leaves macroscopic gravitational fingerprints that don't match simple models. What kind of fingerprint could that be? One possibility is unexpected structure. If the dark sector can cool and clump, it might form substructures much denser than ordinary cold dark matter would allow. That could alter lensing maps. It could change halo shapes. It could create anomalous gravitational micro-lensing events. It could affect the stability and thickness of galactic disks. Another possibility is dissipative dynamics. Ordinary cold dark matter behaves like a collisionless swarm. It doesn't settle the way gas does. But if a fraction of dark matter can dissipate energy via dark interactions, it could settle into a disk. Disks have sharp geometry. They create signature gravitational potentials. They influence stellar motions. If we ever saw robust evidence for a thin, dark disk, we'd have proof of a dark sector that can do more than just drift. And if it can do more than drift, complexity becomes far less far-fetched. But even that still doesn't say alive. It only says structured. So what would count as a stronger hint? Here, the concept of emergence becomes central. Emergence is when a system's collective behavior has properties you can't predict by looking at the components one by one. Water molecules don't have wetness. Wetness emerges. Neurons don't have consciousness. Consciousness emerges. Ants don't have colony intelligence. Colony intelligence emerges. Dark matter halos are enormous. They contain vast numbers of particles. They evolve over billions of years. Even if individual dark particles were simple, their collective dynamics could become complex, especially if self-interactions exist. The halo could behave like a medium with modes, instabilities, flows, and long-lived patterns. If those patterns can store and propagate information within the halo, then lifelike behavior is not obviously forbidden. It is simply outside our current measurement vocabulary. This is where the skeptical voice, your inner scientist, should interrupt and say, okay, but how do we keep this falsifiable? How do we avoid turning it into an unfalsifiable ghost story? That's the correct objection, and the answer is, we don't try to falsify dark life directly. We falsify the prerequisites. We ask, does the dark sector have self-interactions beyond gravity? Does any fraction of it have dissipation, the ability to cool and form dense structures? Does it produce observable changes in halo profiles, collision offsets, disk dynamics, or early universe signals? If the answer to all of these is no, then the dark life idea becomes much less plausible. Not logically impossible, but pushed far into the speculative shadows. If the answer is yes to even one, especially dissipation, then the conversation changes. Because dissipation is what turns a passive swarm into a system that can build complexity. It's what allows chemistry, structure, and long-lived organization. Now, let's confront the psychological grenade hiding under all of this. If a complex dark sector exists, and if it had 13.8 billion years to evolve, then the question isn't, could life arise? The more haunting question is, why wouldn't it? On Earth, as soon as conditions were remotely stable, life appeared quickly in geological terms. That suggests that life is not a freak accident. It's what complexity does when given time and gradients. If that's true, then complexity elsewhere, anywhere, becomes a breeding ground for lifelike processes, which drags us straight into the Fermi paradox in a totally new way. Maybe we don't detect alien civilizations because they're rare, or because they're quiet, or because they're far away, or because we've been scanning the cosmos for conversations made of light, while the dominant civilizations, if they exist, might be built from something that doesn't speak in light at all. That idea is terrifying because it doesn't place them somewhere across space. It places them across a boundary of matter, a boundary that could overlap our own location perfectly. Same galaxy, same solar system, same room in principle. Two layers of reality passing through each other, unable to touch, unable to communicate, connected only by gravity. And gravity is the worst messenger. It's universal, yes, but it's weak. It's like trying to whisper across a stadium while a storm is happening. So here's the cliffhanger we're going to use to keep the viewer glued. If there is any hope of contact, any hope of detection beyond passive gravitational inference, it would require us to treat gravity not just as a force, but as a communication channel. That sounds insane today. We can barely detect gravitational waves from colliding black holes. We cannot generate meaningful gravitational signals at human scales, not even close. But 500 years ago, we couldn't imagine radio. 100 years ago, we couldn't imagine sequencing life's code. 20 years ago, we couldn't imagine AI doing what it's doing right now. The boundary between impossible and engineering is not fixed. It moves when knowledge moves. If the dark sector is complex, and if intelligence could exist there, what would a billion-year head start look like? What kind of technology could operate in a sector we can't see? And most importantly, what indirect signs would it leave in the one thing we can measure? Gravity. Because if the dark universe is alive, it won't announce itself with lights. It will announce itself with patterns. Most people imagine first contact as a message from the stars, a radio whisper, a blinking laser, a mathematical pattern we can decode like a cosmic postcard. But if the dominant stuff of the universe doesn't speak in light at all, then the entire idea of listening has been backward from the start, because there is one force that touches everything, even the things that refuse to glow. Gravity, the oldest language in the universe, the quietest one, and the most terrifying, because it can carry meaning without ever looking like a message. Here is the uncomfortable truth that keeps this idea pinned to science instead of fantasy. If dark matter barely interacts with ordinary matter, then you shouldn't expect it to leave the kinds of fingerprints we're used to chasing. No chemical traces, no heat signatures, no radio leakage, no atmospheric anomalies. None of the familiar biosignatures that we associate with life. If something is living in the dark sector, it could be unimaginably close, passing through your body, coexisting in the same room, overlapping your world like a second transparent city, and you still wouldn't know, because your senses are tuned to photons and electrons, not to whatever the dark sector uses to build itself. So if you want to keep this honest, you do not start by hunting for life. You start by hunting for complexity. You start by asking a question that sounds almost boring, but isn't. Does dark matter have internal dynamics beyond simple gravity? Because complexity is the gateway drug. Complexity is where structure forms, and structure is where information can be stored, transmitted, and transformed. That is the precondition for anything that deserves the word alive, even in the loosest definition. Think about what makes the ordinary universe interesting. Ordinary matter can cool. It can radiate energy away. It can clump into clouds, then into disks, then into stars. It can build chemistry, atoms, molecules, chains, membranes. The entire ladder of complexity exists because ordinary matter has forces that let it interact with itself in rich ways. If the dark sector has anything like that, any dark analog of electromagnetism, any dark radiation, any way to shed energy and settle into stable forms, then the phrase dark structure stops being poetic and becomes physical. And structure doesn't need to mean little beings hiding behind your couch. It can mean something far larger and far stranger. Dark disks, dark clumps, dark compact objects, patterns inside halos that evolve over billions of years. If those exist, they would change the way gravity behaves on large scales in ways we can actually measure. Not measure perfectly, not easily, but measure. That's the key. The moment you can measure it, it becomes science. This is why some of the most powerful tests aren't underground detectors at all. They're the sky itself. When a massive object sits between us and distant light, it bends that light, distorts it, magnifies it. Gravitational lensing is not a metaphor. It's a shadow cast by something you cannot see. If dark matter halos were perfectly smooth and boring, lensing patterns would be relatively clean. But if halos contain substructure, dense knots and ripples and clumps, those leave subtle distortions. And subtle distortions are exactly the kind of place where simple models start to crack. There's a reason this is so unsettling. Because once you begin mapping the invisible scaffolding of the universe, you begin to realize something. The dark doesn't look like an empty background. It looks like an architecture. Not designed, careful, that word is a trap, but structured, evolved, shaped by its own rules over cosmic time. Even if every dark particle is individually simple, a galaxy-sized halo is not. A halo is a dynamical system with history, and history is where complexity hides. Now add a second layer that sounds like pure science fiction until you remember it's just physics with different ingredients. Communication requires a medium. We use electromagnetic waves because we can push charges around and generate light. But if dark matter doesn't couple to light, then any dark civilization, if it exists, would build its entire reality on different carriers. Dark radiation, dark fields, dark interactions we don't yet understand. Their radio would not reach us. Their internet would be invisible. Their cities could overlap our orbit, and we would fly through them like ghosts. So, is contact impossible? Not necessarily. It's just brutally difficult, because there's only one guaranteed bridge between the sectors: gravity. And gravity is weak, which means the only loud gravitational events we currently detect come from absurdly massive collisions. Black holes, neutron stars, the universe's most violent choreography. That makes it feel like gravity is useless for communication. But that conclusion is based on our technology and our scale, not on fundamental law. If you had the ability to move enormous masses with precision, you could, in principle, encode information in gravitational patterns, not as a single burst, but as a long, repeating signature, a rhythm, a deliberate cadence. The universe is full of noise, full of random events, full of turbulence. But a rhythm is different. A rhythm is a claim that something is keeping time. And the deepest question becomes, do we have any clocks sensitive enough to notice a rhythm in gravity? We do. They're not clocks made of gears, they're stars. Pulsars are the closest thing nature has to a metronome, spinning neutron stars, beaming pulses that arrive with astonishing regularity. When gravity warps the space between a pulsar and Earth, the timing shifts. It's tiny, but measurable. Over long periods, patterns emerge. If something produced a persistent gravitational modulation, something repeating, stable, structured, pulsar timing is one of the places it could show up. And here's the critical discipline, the thing that prevents us from turning this into spooky storytelling. A structured signal is not automatically intelligence. The universe can generate periodicity on its own. Orbits are periodic. Rotations are periodic. Resonances are periodic. You never get to shout, "Life," just because you found a pattern. What you do instead is ask, does the pattern match what blind physics tends to create, or does it resist simple explanations? Does it persist across contexts? Does it carry an improbable amount of information density? Does it behave like noise, like a clock, or like a code? That last word, code, is dangerous. It invites imagination to run ahead of evidence, but it's also the honest endpoint of the logic. Because if the dark sector has rich internal interactions, then it might support its own chemistry. And if it supports chemistry, then it supports the emergence of self-maintaining patterns. And if self-maintaining patterns exist, then selection exists. And once selection exists, complexity has a direction, not a purpose, not a plan, but a tendency to climb. The same ladder that got from amino acids to neurons could exist in another material alphabet. Some people try to reassure themselves by saying, even if dark complexity exists, it would be too diffuse, too cold, too inert to do anything interesting. But that reassurance is an emotional guess, not a scientific conclusion. We do not know the dark sector's temperature in the sense that matters for complexity. We do not know if it has dissipative channels. We do not know if a fraction of it can collapse into dense structures. We don't even know if we're thinking about the right categories. Every time we assumed simplicity because it felt neat, the universe punished us with a new layer of weirdness. There is also a quieter implication that almost nobody thinks about because it doesn't sound dramatic at first. If the dark sector is complex, then it is not just out there in the void. It is braided into the places where structure forms, galaxies, clusters, the very scaffolds where stars ignite. The visible Milky Way is not floating alone. It sits inside a dark halo, like a lantern inside a vast, invisible cathedral. If any fraction of dark matter can cool and clump, then the densest regions might align with the places where ordinary matter also becomes organized. Not because the dark wants to follow the light, but because gravity herds both into the same general arenas. That possibility is what makes the whole idea feel personal. Not aliens far away, but neighbors in the same address of space-time. Two ecosystems, two chemistries, two histories, occupying overlapping volumes without contact. It's not paranormal, it's just what happens if the universe has more than one way to build complexity. And those ways don't talk through light. At this point, a skeptical mind will push back with the right objection. If dark structures existed near us, wouldn't we notice their gravity? Wouldn't their mass tug on planets, disturb orbits, warp local motion in obvious ways? And the reply is subtle. Dark matter's gravitational influence is clear at galactic scales because there is so much of it. Locally, within a solar system, the amount in any given volume is small compared to the mass of the Sun and planets, so you don't expect dramatic tugging. The dark can dominate the universe and still be whisper quiet in your neighborhood. That does not make the idea safe. It makes it harder to kill. Because the absence of obvious local anomalies doesn't rule out a vast, slow, structured dark architecture on scales where our measurements are still incomplete. The honest position is not, it exists, and not, it doesn't. The honest position is, the simplest story has been failing, and the alternative story invites a kind of complexity that we can test indirectly. And the moment you open the door to a complex dark sector, you open the door to dark emergence. Emergence is the universe's favorite magic trick. Wetness is not in a single water molecule. A thought is not in a single neuron. A tornado is not in a single air particle. They are patterns that appear when enough simple things interact under the right rules. A galaxy-sized halo, evolving for billions of years under rules we don't fully know, is exactly the kind of system where emergence could show up in forms we wouldn't anticipate. That is what makes the question scientifically legitimate. Not, are there invisible beings, but what kinds of higher-level behaviors can a dark, dynamical system exhibit? And if you let yourself stare at that question long enough, another idea creeps in, quietly, almost politely. If dark intelligence existed and wanted to remain undetected, it wouldn't need to hide. It would already be hidden by physics. It wouldn't need stealth technology. It would simply be made of the wrong kind of matter for our senses. The greatest camouflage is not a cloak. It's being constructed out of a material your enemy cannot perceive. But enemy is the wrong word. The terrifying version is not invasion. The terrifying version is indifference. A civilization older than ours by billions of years may not care about us the way we don't care about bacteria drifting through the air, real, alive, complex, and irrelevant to our day. Not because they're cruel, but because scale changes what counts as significant. We could be shouting into the cosmos, and the cosmos could be full of minds that never even register the sound. There is still one more twist that turns this from cosmic philosophy into something you can almost feel in your bones. We have been trained to think of reality as what we can touch, what we can see, what we can record. But physics has been trying to tell us for a century that reality is deeper than sensory comfort. Most of what exists does not announce itself to your eyes. If the dark sector is complex, then the majority of reality is not merely invisible mass. It is a potential domain of structure, history, and perhaps even experience. And that shifts the mood completely. The universe stops being a stage with empty black curtains. The darkness becomes the main room, and we are the small lit corner where matter happens to glow. You are not looking out into emptiness when you look at night. You are looking into the dominant substance of existence, and you do not yet know what it is capable of. When you close your eyes, you see darkness, a simple flat black behind your eyelids. But that black is not emptiness. It is the closest visual metaphor you have for the deep majority of the cosmos, present, surrounding you, pressing gently through gravity, shaping everything without ever showing its face. If there is a secret hiding in the universe, it is not hiding in the distance, it is hiding in the invisible. And the most unsettling thought is this: we may already be living inside it. You are here, still in the same room, same walls, same ceiling, same familiar weight of ordinary life. And yet, after everything we've traced, it's hard to shake the feeling that familiar might just be a trick your senses play to keep you calm. Because if most of the universe is made of something you can't see, then you've been living your entire life inside an ocean without ever feeling the water. Let's land this with honesty. We do not know what dark matter is, not yet. We know it exists because galaxies behave as if they are embedded in invisible mass. We know the simplest candidates have been hunted for decades and keep slipping through every net we throw. And we know that physics has started taking seriously a possibility that used to feel like science fiction. The dark sector might have more than one ingredient, more than one force, more than one way to organize itself. That's not a claim about aliens. That's a claim about complexity. And complexity is the one thing the universe never stops producing, given time and rules. So what would it take to move this from haunting idea into testable science? The answer is surprisingly grounded. We keep tightening the constraints. We keep mapping the invisible with gravity. We keep watching how galaxies bend light. We keep measuring how structures grow across cosmic time. We keep listening for tiny timing shifts in pulsars. We keep building detectors that rule out the easy answers. Because when the easy answers die, the real answer gets cornered. Science isn't a single dramatic discovery. It's a slow siege. And here's the part most people miss. Null results are not failure. Null results are the universe telling you, not that. And every not that is a door closing on simplicity. When the universe refuses to be simple, it doesn't mean it's mystical. It means it's richer. It means the scaffolding we're standing on might be built from a deeper architecture than our senses can directly detect. That's why this story matters, even if dark life turns out to be wrong, because the bigger point survives. Reality is larger than what glows. But let's not dodge the main nerve of the idea, the one that makes your stomach go a little tight. If a complex dark sector exists, then a form of dark chemistry is not forbidden by any known law. And if dark chemistry is possible, then self-maintaining patterns are possible. And if self-maintaining patterns exist long enough, selection becomes possible. And once selection exists, complexity can climb. Not guaranteed, not destined, but possible. Possible in the same brutally simple way life became possible on Earth, because the rules allowed it, and time did the rest. That's what makes this question feel like it's staring back at you. The alive part is not a romantic leap. It's the uncomfortable continuation of the logic. It forces you to ask something that sounds almost philosophical, but is actually scientific at its roots. Are we mistaking visibility for importance? Are we confusing what we can perceive with what is most real? The universe has embarrassed us with that mistake before. There's another angle that is even more personal and weirdly hopeful. Humans have spent centuries looking up and asking, are we alone? And the silence has done something to our psychology. It's made us feel like consciousness is rare, fragile, a candle in a cold tomb. But what if the silence isn't emptiness? What if it's simply that we've been listening in the wrong channel? A conversation could be happening all around us, written not in light, but in a kind of physics we have not learned to sense. You can treat that as a scary thought, or you can treat it as a humbling one, because humbling is just terror that learned manners. If the dark sector is complex, then existence has more ways to exist than we assumed. Minds, if they arise there, would be minds unlike ours, not just in culture or technology, but in material, in the very substrate of being. They might have senses we can't imagine, timescales we can't relate to, priorities we'd never recognize. They might not even experience the universe in frames, in scenes, in moments. They might experience it like tides. And that brings us to the most honest ending. We do not need to decide whether dark matter is alive today. That would be pretending. What we can do is accept that the question is no longer absurd. It's not a bedtime ghost story. It's an invitation to take the weirdness of the universe seriously, without worshipping it, without sensationalizing it, without turning curiosity into clickbait. The universe is already dramatic. Our job is to not lie about it. So here's the real takeaway you can keep after the screen turns off. When you look at your hands, you're looking at a tiny minority of reality. When you look at the night sky, you're looking at the lit foam on the surface of a deep cosmic sea. The majority of existence does not shine. It does not announce itself. It shapes everything anyway. And if the dark is complex, if it can form structure, then the dark may have its own story running in parallel with ours, in the same universe, under the same gravity, inside the same silence. That thought is heavy, but it's also kind of beautiful, because it means reality is not exhausted by what you already know. It means discovery is not done. It means the universe is still keeping secrets, big ones. And we are alive at a time when we finally built the tools to start prying those secrets open. Not with superstition, with measurement, with patience, with the stubborn refusal to accept it looks empty as proof that it is. Now, before we close, try a simple experiment. Don't change anything about your room. Don't move. Just notice how easy it is to believe the world is exactly what it seems. And then remember, everything you see is the exception, not the rule. The rule is darkness, and the darkness is everywhere. If it turns out to be nothing more than silent particles drifting forever, that's still astonishing. But if it turns out to be a domain of complexity, of structure, of something that can evolve, then the universe is not just stranger than we imagine. It is stranger than we are currently equipped to imagine. And that's the moment where science becomes something emotional, not sentimental, just real. Because you can feel in your bones what it means to live inside a reality that is mostly hidden. It makes you smaller. It also makes you part of something bigger than your fear. The dark doesn't have to be an enemy. It can be a frontier. If this video stretched your mind even a little, if it made you look at the night sky and feel the darkness differently, then help it reach someone who still thinks space is just empty. Share it with a friend who loves big questions. And if you want more science that doesn't insult your intelligence, subscribe and turn on notifications, because the universe is not done surprising us. Until next time, remember, what you can see is only a sliver. The rest is waiting.